All right, next up in section 13.5, we're going to look at question number 4 from the worksheet. So here, number 4 says that the capacity C of a communication channel, such as a telephone line, to carry information depends on the ratio of the signal strength S to the noise N. This relationship is described by the equation C is equal to the log of 1 plus S over N. Suppose that the signal and the noise are given as functions of time t seconds. By S of t is 4 plus the cosine of 4 pi t, and n of t is 2 plus the sine of 2 pi t. What is the derivative dc dt 1 second after transmission started? Is the capacity increasing or decreasing? Okay, so here we have this quantity C, the capacity, and it depends on these quantities S and N, right, the signal and the noise, and then those depend on time, okay? And so what we ultimately want is the rate at which our capacity changes with respect to time. So we want dc dt 1 second after transmission is started. So we want that derivative at t equals 1, okay? And just like we've been doing, right, we can compute that using the chain rule. So we're looking at these intermediate rates, del C del S and ds dt. And then we also would have del C del N and dn dt. All right, so here I'll just write down the expression for the derivative dc dt, and that's just the usual thing here. I'll take the product of those rates in blue, del C del S, ds dt, plus del C del N times dn dt. And let's go ahead and compute some of this stuff, right? So we have, again, our function for C in terms of S and N down here. So if I want to compute the derivative of C with respect to S, well, I'm differentiating a log, so that's going to give me 1 over what's inside the log, so that'd be 1 plus S over N down here. And then I'm going to multiply by the derivative of what's inside the log with respect to S. So N here is just a constant, so that derivative would just give me a 1 over N. Okay, so that part is just the del C del S. And then I'm going to multiply that by ds dt. So here's my function for S in terms of time. So I'm going to differentiate the cosine. That's going to give me a negative sine of 4 pi t. And then I'm going to multiply by 4 pi from the chain rule. Okay, great. So that is this first product. And then I'm going to go ahead and add to that the product of del C del N and dn dt. So del C del N, really similar, 1 over 1 plus S over N. But now I'm going to have to multiply by the derivative of what's inside the log with respect to n, right? And so S now is constant. This is really n to the negative first power. So its derivative would be negative n to the negative second power. Or put all together, we're going to get minus S over n squared. Okay, then I'm going to multiply by the derivative of n with respect to time, and that's going to give me cosine of 2 pi t times 2 pi from the chain rule. Okay, cool. So these two terms are the second product there. All right, now basically what's left? Well, I ultimately want that derivative when t is 1. Now I could go ahead and clean all of this up, and I will do a little bit of simplifying, but we actually are not going to have to get too crazy with that, because since I want the derivative at a specific time, I can basically plug stuff in, then simplify, and simplifying a numerical expression is certainly going to be easier than going through all of the algebra. Okay, so let's go ahead and we will do a little bit of cleaning up. I'm going to put for this first product just this the sine and the 4 pi upstairs. So I'm going to get minus 4 pi sine of 4 pi t. Then down in the denominator, okay, I'm going to multiply this n here off to the right. I'm going to multiply that in, and that's going to give me an n plus ns. All right. Now for the second product here, pretty similar. I'm going to move the cosine, the 2 pi, and there's that s. That all is going to get moved to the numerator, and this negative I'll just put out in front of the fraction. So this would be minus 2 pi cosine of 2 pi t times s. And then we're going to divide that by, well, again, I'm going to go ahead and distribute, in this case, the n squared, and that's going to give us downstairs an n squared plus what? Well, we'd lose a factor of n, so I'd be left with an s times n. Okay, now I could go ahead and combine all this if I wanted to, right? But that's going to be just too much work, okay? Instead, what I'm going to do is just plug in 1 for t, because this is really what we want, the derivative of c with respect to t, 1 second after transmission starts. And one thing that immediately jumps out, look, I'm going to get the sine of just 4 pi for this first term. And the sine of 4 pi is 0, so that's awesome. That whole thing will just drop out. For this next part, I'm going to get what? Well, minus 2 pi. The cosine of 2 pi is 1. That's nice. And then I need to know what s is and what n is to finish. And we can answer that by just using our functions for s and n. So let's do that, say, up here. We can say that when t is 1, okay, s of 1 is going to equal 4 plus the cosine of 4 pi. Cosine of 4 pi is 1, so 4 plus 1 would be 5. Okay, n of 1, this is going to be 2 plus the sine of 2 pi. Sine of 2 pi is 0, so that's in fact just going to give us 2. Okay, so now what I'm going to do is just plug in these values for s and n. So I'm going to get a 5 up here. Downstairs I'm going to get a 2 squared, and then s is 5, and that's going to multiply the n, which again is 2. And so then we will add those up. All right, and so now what are we going to get? A minus 10 pi in the numerator. The denominator would be 4 plus 10, which is 14, and then that simplifies to minus 5 pi over 7. Awesome. Okay, so that would be the rate of change of our capacity with respect to time, 1 second after transmission started. And then when it asks, is the capacity increasing or decreasing? Well, since this derivative is negative, right, we can say that C is decreasing at 1 second, right, when t is 1. All right, that is going to do it for this problem. I'll see you next time.